Hey everyone, welcome back. In this video we're going to cover this particular problem right here. So we just have a simply supported beam that has one load applied to it, and what we want to find is the reaction forces at these two places here, at these supports. So just so we have some kind of conventions, we can call everything. This will be support A, that'll be support B, and we'll just call this point of force application C. Alright, so in statics, the kind of main equation that you use is the sum of all forces set equal to 0. So in this situation, if we break our forces into y, break our forces into x, so what we do here is we know that we have a, let me just set some positives and minuses here. So here we have the negative 6 kilonewtons, and we have a positive RB, which is the reaction force pointing up at B, and we have a positive reaction force at A. So that means that when we're pushing down with this force here, the supports here we're just kind of assuming are pointing up. And so that's everything for the Y direction. In the X direction, we got nothing. So the only thing we have is this support going down, or sorry, this force going down, and the two supports going up. So what we have here is one equation and two unknowns. And if you remember from algebra, you need at least the number of equations that you have unknown. So since we have two unknowns, we have to have at least two equations. So the other thing we can do in statics is we can say the sum of all moments is equal to 0. And when we do that, what we do is we say, okay, well at point A, we're going to take the moment arm around that and say that all the moments have to equal 0. So if we use this as our reference point, and we're going to assume that counterclockwise is positive. You see that common in a lot of engineering courses, that counterclockwise is positive. But it really doesn't matter as long as you're consistent. So we're taking it around point A. So we have our force of 6 kilonewtons, and that is 3 meters away. Now I'm keeping the units out here for just ease, convenience, but we're keeping in kilonewtons and we're using meters. In the end, any forces we're trying to calculate, the meters will cancel out and you'll just get kilonewtons. So just wanted to be clear about that. And so that's the moment around there, but it's pointing in the clockwise direction. As you can see, if I pivot here and I push down here, it's going to want to rotate this thing clockwise. So it's a negative. And we also have our reaction force at B that is pointing up, or at least that's what we're assuming right now. And so it's going to make it want to rotate counterclockwise, which we said is positive. And that is 5 meters away. And now, as you can see here, we have just one unknown in this equation. So what we can do is we can just solve for that. So we have RB times 5 equals plus 6 times 3, which is equal to 18. And then, so sorry if this is getting a little messy. So we have RB is equal to 18/5. So what number that comes to, I don't know, but I will let you know in a sec. So we have RB calculated, and up here we already had an equation with RB in it. So what we can do is we can say RA is equal to 6 minus RB. As you can see, I just kind of did the algebra real quick. And we know what RB is, so it's actually 6 minus 18/5. Alright, so I pulled out my calculator, ran the numbers, and what we found before was that RB was equal to 18/5, RA was equal to 6 minus 18/5, and that came out to 3.6 kilonewtons for RB and 2.4 kilonewtons for RA.